So we've looked at non-coherent detection for PSK, and if the phase is slowly changing enough, we could use a clever differential method. If it was not changing slowly, we could have used a square law detector. But in FSK, for non-coherent detection, we will definitely use a square law detector. So if the coherent receiver had the form we'd seen previously, where there was a branch for each one, and each branch of the correlator, each branch of the receiver was a correlator, which essentially is calculating the coefficients of the received signal. In this case, remember, we assume that the phase is known, so that when we're correlating with the known signal, that's with the phase that has been followed. Now, if we were going to look at the non-coherent version, we could indeed calculate the coefficients with an I and a Q in each branch. And then we could square each branch, and we could sum those two branches. And we know that in this case, we have calculated the energy in that signal. So this would be using the coherent receiver structure to see the operations that would be necessary to get at an energy. And if we would get an energy in each one of the branches, and then our decision stage would just say, choose the branch with the most energy. So if we didn't know the phase, you know, you can think of this as being like, sort of like, you know, that cosine squared plus sine squared is going to always give you 1, no matter what the phase is. So this is sort of the strategy that is behind this, that there is an unknown phase. I know if I'm just in the cosine branch, it could go through 0. If I'm just in the sine branch, it could go through 0. But if I sum the squares of the two, I'm going to get something that is not varying with the phase of my oscillator. So I have a local oscillator. It's not like the differential PSK, because I do have a local oscillator, but this time the phase is free running. I'm not tracking it to make it like the phase of the transmitter. But when I'm looking at my decision stage, instead of looking at the output right here at the coordinates, I'm looking instead at the energy. So this is a construction for the receiver, which is sort of to help appeal to your intuition. But it's not what we would actually construct, because the whole point in doing non-coherent detection is generally to make a simpler receiver. And this doesn't look simpler, it looks more complicated. But don't be distracted by that, because we'll see that the actual form of the receiver will be simpler. But from a logical point of view, this is the strategy we're doing in general. Get the energy, compare the energy, choose the branch with the most energy in it. So what do we actually do instead of this sort of cumbersome receiver? Well, what we do is, these are different frequencies. So what we can do is a filter bank. So we have here a filter bank where we take each one of the frequencies and we say, is there energy inside of this passband? And the way you see if there's energy inside of the passband is you just do an envelope detector. You don't care about the oscillations in the carrier. You're just looking to see if there's energy. And then once again, the decision stage is just choose the one with the most energy in it. And so you can see that this form is much simpler, very easy to implement. In fact, the envelope detector can be a simple RC circuit with a diode. And so while there may be some high frequency carrier here, it could be on a 1 gigahertz carrier, if we look at the envelope of them, you know, this will track the actual data rate, and you can tune the RC to make sure that you're got something commensurate with your data rate. So let's look at the simple case. So let's see now what's going on with this envelope detector. So let's take the simple binary case. So we have two filters. And the output is two decision statistics, Z1 and Z2, and we're going to pick the largest. And what are these decision statistics? So let's consider the two cases. In the first case, when symbol 1 is sent, and the second case when symbol 2 is sent. Well, in the case of symbol 1 sent, in filter bank number 1, we will have a signal which is proportional to the square root of the, proportional to the amplitude, which will be the square root of 2EB over T, plus the noise in the envelope detection. And in the case of when S2 is sent, then Z2 will be what this is. Excuse me, the expression that we see here. And of course, if S1 is sent, what would Z2 be? Well, I guess I could say Z2 here would just be noise. And in the case S2 is sent, Z2 would be noise plus some signal, but Z1 would just be noise. Okay, so I hope this is clear. When S1 is sent, then Z1 has got noise plus something, and Z2 is just the noise. And now when S2 is sent, then the second filter has got something, a signal in it plus noise, whereas the first filter has just got noise in it. And so that's why we say choose the largest is the good strategy for detection. Now, when there is no signal, okay, so let's look at the case where we're looking at Z1, but it was S2 that was sent. So in this case, it's just the noise. In this case, the statistics for the noise for an envelope detector, you can look it up in a textbook, is what we call Rayleigh noise, and it has the Rayleigh distribution. And so the conditional probability density for Z1 under the condition that S2 is sent is given by this probability, which is basically Z1 times an exponential of the negative Z1 squared. So if there was no multiplying Z1, we would have Gaussian, but because it's multiplied by Z1, this is instead a Rayleigh distribution. And it's a one-sided distribution. Of course, it can't be negative because we're looking at the positive envelope. Now, if I look in the other case where there's no signal, so Z2 is sent, S1 is sent, but I'm looking at the second filter. In that case, of course, it's the exact same distribution by symmetry. It also is Rayleigh, but now we're looking at Z2. Now, what happens when we have signal present? Well, when we have signal present, the statistics at the output are, instead of a Rayleigh distribution, we get a Ricean distribution because we have a Rayleigh distribution, but offset by the amount of the energy in the signal. So the Ricean distribution uses the Bessel function that you see here. And so the parameter that we see two parameters here in the Ricean form. Let me go back here to the Rayleigh one. In the Rayleigh, there was one parameter, which was the variance. But in the Ricean, we can see that we have the variance and a second parameter, which is this mu, which I tell you is the square root of EB over T. So this has to do with the amplitude of the signal as it's going through the envelope detector. And so we have the, looks like the Rayleigh distribution here, but now we're multiplying by this Bessel function. So things look a little complicated, but here's, by the way, here's the Bessel function in case you've forgotten the definition of that function. So things are complicated, and so it's not as easy as the Gaussian noise case. I did plot for you here the distributions just to get a feel for what it looks like. So if I call K the ratio of mu to sigma, so here the mu, which is the square root of 2EB over T, and sigma, which you can imagine is related to the variance of the noise. And so this ratio, K of mu to sigma, is kind of like a signal to noise ratio. It sort of looks like a signal to noise ratio. And in the case of letting the signal go to 0, so there's like no signal, just noise, then the Ricean distribution becomes a Rayleigh distribution. And so when I see in blue here k equal minus infinity in dB, when it goes to 0, I have this form of the Rayleigh distribution. And as the signal gets stronger and stronger, the Ricean distribution is moving more and more to the right away from the origin. And it's just easier to tell the difference between, signal present, signal not present, the stronger the signal is. And this, of course, is quantified, and I can use these distributions to actually calculate the probability of error using the conditional probabilities, just as we did in the case of Gaussian distribution, except that I would have to do my averaging now over the Ricean and the Rayleigh distributions. And so if I were to summarize the conditional densities, we have the probability of Z1 condition on S1 is Ricean with this parameter, and Z2 given S2 is Ricean with the same parameter. And when the opposite case is we have Rayleigh. And so, if we go back to what we did in the binary case with Gaussian, I would use the exact same equations to describe this system, but I would average over a different PDF. And so, in fact, this is the equation that would be 1/2 the probability of error of one kind and the other kind. So here's the probability of error when S2 is sent, when S1 is sent, and of course the total probability of error is 1/2 of the sum of the two kinds of errors when an S1 is 10 and S2 is 10. And of course, when does the error occur? Let's have a zoom in on one of these. Well, if S1 is sent, then I'm going to make a mistake when Z2 is greater than Z1, because if Z2 is greater than Z1, I'm going to choose 2, but 1 was sent. And so right away you can see just from the first equation that there's a lot of symmetry here, and I just show you the conditional probabilities, and that in fact 1/2 plus 1/2, it comes up to be, just look at one of them. And so it doesn't matter which one, we just pick one. So the probability that Z1 is greater than Z2, given that S2 was sent, is the probability of error. And so if I want to calculate this probability, I have to get rid of the condition by averaging over the conditional density. So here's the probability. I average over that condition, and so I end up with an integral of this form. And so you can see that in the Z1 given Z2, we have a Rayleigh, which I integrate over Z2 to infinity, and then here I have a Ricean. So looks really awful, right? Well, when you have time and nothing to do, I'll let you look at the math, but you can actually, this collapses very nicely into a super simple form. And in fact, the probability of error for non-coherent detection is just an exponential, a decaying exponential. So very simple form. Won't go through the math, but take my word for it, this is what you come out to. So for non-coherent FSK, we get something very similar to what we saw for DPSK. And that is that there's about a 1 dB penalty when we use non-coherent reception for the binary case than when we use coherent detection. And again, we get a very simple, inexpensive receiver when we use this non-coherent reception, and the penalty is very moderate, just 1 dB. So we could look at the bit error rate curves, so you get a feel for these, and we have here the PSK and here the FSK. And in the case of PSK, or either of them, you can see there's this 1 dB distance between the two curves. And the PSK is antipodal signaling, and this is orthogonal signaling. So for binary, we know that the PSK is better. And here we have the equations, and you could go into MATLAB, for instance, and plot this Q function or plot this exponential, and you would get the curves that I've plotted here. That's exactly what I did in order to get these curves.